Okay, so we are going to go through the rest of 7.2 and then 7.3 and 7.4. Then we're going to start chapter 5. At this point, my goal is to still have your test on the 26th. So I'm going to go through this stuff. Yesterday we talked about, or in class on Tuesday, we talked about one-to-one and onto functions. And if a function is both one-to-one and onto, it's called bijective, or it has a one-to-one correspondence. And we sort of talked about those like pieces of paper fitting together perfectly, like on top of one another. And so we're going to sort of continue that idea. Now we're talking about inverses. So in college algebra or in any other class where you talk about inverses, you really didn't talk about a codomain. You were talking about just a domain and a range. And so, you know, what we needed for a function to have an inverse, wow. For a function to have an inverse in college algebra, basically it just needed to be one-to-one, not onto. But now, because we actually have a domain and a codomain, right, which is not necessarily equal to the range, for us to be able to talk about an inverse function, so a function going this way, remember everything in our domain has to map somewhere. So if that's true, for our inverse here to be a function, everything over here has to map somewhere. That means under the original function f, everything got hit. So the original function f has to be onto in order for f inverse to work because everything in the domain has to go somewhere. So for a function to have an inverse, f actually needs to be one-to-one and onto. The one-to-oneness, means that every input goes to one output, and not two outputs. So if it wasn't one-to-one and you had like this sort of thing happening where these both went somewhere, then on the way back, that wouldn't be a function anymore. So you need both the one-to-oneness and the onto-ness for it to work. So if a function is both one-to-one and onto, the inverse function of f is the function that assigns each element of y to the unique element in x where f of x equals y. The inverse function is denoted f inverse from y to x and has the property that f inverse of y, this is a thing that you know, is x. And then when that happens, we say that f is invertible. So for a function to be invertible, it has to be one-to-one and onto. All right, so we have these questions on number 8 here. Is this function from r to r that's given by f of x squared invertible? We decided that that this wasn't one-to-one or onto. Remember, we wanted for it to be onto, we can only hit non-negative real numbers when we square them. So the domain doesn't equal the codomain, so it's not onto. And also the one-to-oneness, like -2 and 2 both go to 4, which is a problem for the way back for the inverse. So this is not one-to-one or onto, so that doesn't work. However, if we restrict the domain and the codomain, it does, right? So you have every input goes to exactly one output, and every output came from exactly one input. You get this thing where you have the onto-ness and the one-to-oneness. So this is a yes. We did prove this, or we talked about it earlier in the packet, so you can look back. F inverse here of x is the square root of x. F inverse of y, we should say, is the square root of x. Okay. And then we have this example for like potato diagram. You have a set ABC that's mapping to a set 1, 2, 3. A goes to 2, B goes to 1, C goes to 3, and that does work. So that is both one-to-one and onto. So it is invertible. All right. Now for composition of functions, which is everyone's favorite topic in college algebra, we have this a function f from x to y and g from y prime to z. These are functions so that the range of f is a subset of the domain of g. So this is big X, this is big Z. I think this is Y. The range of F is a subset of the domain of G. The range of F is a subset of the domain of G. So this is Y prime, I guess, and then there's a Y in here. But this is the codomain is just Y, so we'll just go with this. And then Y prime is sitting inside of here, and that's the domain of G. Oh, I don't know how to make that closer there. Okay. So the composition G of F, so this is your function F, and this is your function G. And remember that this is going to then be from X to Z, and G of F, remember it goes like this. So you work the inside thing happens first. That's why F is first here. All right, so you have F happens and then G happens, and you end up moving from your original set X to this final codomain Z there. All right, so if you're tracking a point in here, X is there, F of X is right there, and then this is G of F of X. All right, so if F from X to Y is invertible, F inverse from Y to X is the inverse of F, then the composition of function things, this works where you can compose them. F of F inverse of Y is just Y, you get back what you started with, or F inverse of F of X is just X. So this is sort of how you know of inverse functions, they undo the original function. So that's still true now. Okay, so on your homework, I don't know that you're necessarily going to prove this, but you are going to confirm or prove that there are two functions that are or are not inverses of one another, because you're going to actually compose them and see if you get back what you started with. Okay, so we are going to do this exercise 9. We're going to show that the composition of two one-to-one functions is one-to-one. So this is kind of fun. I'm going to do some scratch work to set this up. So I'm going to give us a potato diagram first. Hopefully Notability's got what I'm trying to do this morning here. Come on now. No, I don't want my potato to be sideways. Sorry, hold on. I got this. There, oof. Okay, so we got 3 potatoes here, and we're trying to say that the composition of two one-to-one functions is one-to-one. So we've got a function f here and a function g here. We're going from x to y to z, let's say. And we're going to assume that f and g are one-to-one. And we want to show that g of f is one-to-one. Okay, so this is our goal, is to show g of f is one-to-one. And the way you show a function is one-to-one, remember, is that you pick 2 things in the domain. So you're going to let a and b be in x. And you're going to assume g of f of a equals g of f of b. And you would like to show eventually that a equals b. So the darts landed in the same spot on the dartboard. You want to actually confirm that they were the same dart. All right, so we're going to write a proof. We'll actually prove that. We will do the work in the proof in a minute. But this is sort of the idea. We want to show this function that goes like from here to here, which is g of f, is 1 to 1. All right, so we are going to let f from x to y and g from, say, y prime to z just call it y to z, be one-to-one functions so we're going to let a and b be elements in x and assume that g of f of a equals g of f of b. Okay, so I'm going to go back over to this diagram. We've got a and b that are over here, right? We're going to confirm that they're the same spot, but right now, whatever, they're right there. Here you have f of a and f of b, and here you have g of f of a and g of f of b. Now, you're looking at here, these two elements are sitting inside of the domain of g, right? And their target is the same. But since g is 1 to 1, and these two darts landed in the same spot, they're actually the same dart. So these are equal to one another. So since g is 1 to 1, we have f of a actually equals f of b. It's that input, call it xy if you wish, or whatever, but you know, g of a thing equals g of another thing, c and d, say. And since g is 1 to 1, c and d are the same dart. Well, c is f of a and d is f of b. So f of a equals f of b. And further, f is 1 to 1. Thus, a actually equals b. So since a equals b, whenever g of f of a equals g of f of b, g of f is 1 to 1. Okay, so that is, I mean, it looks a lot harder than it actually is, but if you're composing two one-to-one functions, the one-to-oneness is not broken under that composition, which is good. The one-to-oneness is preserved by the composition, so that's a good thing. All right, more. We have here on B, we have G from A to B and F from B to C. They're functions. We want to show that F of G from A to C, if F of G from A to C is onto, then F is also onto. Again, I'm going to sketch a diagram so we know what sort of is going on here. Well, I mean, to help us understand what's going on. So just not going to be perfect right now. Okay, so we have G from A to B. Oopsie daisies, I didn't mean to do that. G from A to B. And then F from B to C. If F of G is onto, so that's this thing, is onto, then is F onto. Okay, so we want to show, we get to assume F of G is onto, and we want to show that F is onto. So when we do an onto proof, we're going to pick C. Can I pick I don't want to do a little c because then it won't be obvious. Maybe I just will anyway. Pick little c and big C and show there exists a little b and b where f of b equals c. That's the how you do an onto proof, right? You pick an element in the target, show that it got mapped to by something, show that there is something in its domain that maps to that thing. All right, so we have this C and C. And since f of g is onto, there is a little a and big A, such that f of g of A equals C. Well, g of A is an element in B. So let g of A equal B, say. And f of B equals C, and we did it. Hopefully we'll explain that more in this proof. All right, so we are going to let g from A to B and f from B to C be functions. And assume f of g from A to C is onto. Now let C be an element in big C. Since f of g is onto, there is an A in A such that f of g of A is equal to C. Thus, f of g of A equals C. Notice g of A is actually an element in B. So we'll let B equal g of A. And we have found B in B such that, oh, don't put that in your proof, sorry. Such that f of B equals C. Thus, f is onto whenever f of g is onto. All right. Moving on. If f and f of g are onto, does it follow that g is onto? So prove it. If not, find a counterexample. F of g, so g is first. Oh my gosh, I'm gonna redo that thing. Okay, so you have, we have to think if this whole thing, which is f of g, is onto, we just proved that that means that this one has to be onto. So the question is this one also onto, the first one? And the answer is no. Basically, these two things can sit on top of each other like paper and match up, and that's fine. But this doesn't have to hit everything in here. So let's try to maybe explain this. I'm going to draw the counterexample and then we'll talk about it. So this is your set A, this is your set B, and your set C. If you have an element over here, A, and it maps into, but not onto this set, call this B1. And let's suppose we have another element, B2, that's not hit. Can we still make F and F of G onto? Okay, so let's say we have just one thing over here, and both of these guys go there. All right, so for F of G to be onto, that means that for every C and, oh boy, for every C and C, there is an A and A, such that F of G of A equals C. So does every element in our set C have a pre-image in A? Yeah, you can trace this back all the way to A, and that's fine. And then for F to be onto, that means that for every C in C, there exists a B in B, such that F of B equals C. So does every element in C have a pre-image in B? Yeah, at least one. So we're good there. But B2 doesn't have a pre-image under the function G, right? So A misses it. A doesn't hit this. A is a little piece of paper that stacks up on B like this, not on the edges. So this B2 doesn't have a pre-image. So G doesn't have to be onto. So this here is our counterexample. So no, G does not have to be onto. Okay, let's keep going. All right, now we're on cardinality. Oh, we're talking about cardinality again, and we're gonna use it to actually talk about the thing Whitney was hinting at in class the other day. So y'all, we did cardinality before. If a set has exactly n distinct elements, that's the cardinality of S. But if it has n of them, then it is finite. And if a set is not finite, then it is called infinite. So we're going to talk about the cardinality of each of these sets, and then we're going to talk about infinity. So the cardinality of this set is just 1. The one element in there is just A. The cardinality of this set is also 1. The element in there is the set containing A. The cardinality of this set is 2. Your elements are A and the set containing A. And the cardinality of this set is 1, 2, 3. The sets are A, the set containing A, and the set containing A, and the set containing A. Really weird. But yes, those are your 3 elements. So cardinality, that's the sort of the topic about cardinality. This is a really strong definition that if you have any 2 sets A and B, A has the same cardinality as B, if and only if there is a 1-to-1 correspondence between A and B. Remember, this is a bijection. And the fact that this is an if and only if statement means that if you have a bijection between 2 sets, then you know they have the same cardinality. Or if you know 2 sets have the same cardinality, then you can come up with a bijection between them. So this if and only if, I mean, this is good. If you know one thing, you know the other. And so that's really powerful. And symbolically, this looks like this. The cardinality of A equals B if and only if F from A to B is a bijection or a 1-to-1 correspondence. Okay, so we're going to decide if these pairs of sets have the same cardinality, and if they do, we're going to find a bijection between them. So, and if they don't, we're going to explain why not. So these 2 sets have the same cardinality, right? The cardinality of A is 4, and so is the cardinality of B. So let's come up with a function between them. that is both 1-to-1 and onto. So we're looking at A, B, C, D here, and then W, X, Y, and Z. And we're just gonna boop, 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 boop. There is a 1-to-1 correspondence between those two functions. I mean, those two sets. That's a 1-to-1 correspondence between the two sets. Now you can tell we can't do that on this one, right? Because the cardinality of X is 3 and the cardinality of Y is 4. Whoa. So if we tried, let's just do it for good measure. If we tried, we either can't hit everything, or if we were trying to go the other way, because it should work either way. It doesn't matter what if it's A to B or B to A. So either it's not onto, or it is not 1-to-1, depending on which way you set up the which in the bigger set is on of your function. So if it's the domain or the codomain. So when they don't match up evenly like that, those pieces of paper we were talking about, then things get weird. If the top piece is smaller, then some stuff doesn't get hit. If the top piece is bigger, then some stuff gets hit twice. So one breaks the 1-to-1-ness and one breaks the on-to-ness. All right. So now we get to talk about infinity. So Z and 2Z, this is the even numbers, the even integers. I'm going to scoot this over here because I'm probably going to need that space. And I'm going to start writing in a different color. Okay, so this is trippy and probably the trippiest thing we have done so far, but these are actually equivalent. And it doesn't feel like that they should be, right? Because the integers is all of the integers and the even integers is just the even ones, but there are the same number of them. These are both countably infinite. What that means basically is that you could start listing them. And if you could forever talk, you would be able to list all of them. They are called countable because you could, actually count them. And when you can count a set, that means it has the same cardinality as the integers because that's counting. So we are going to come up with a function. This means that we could, to prove that these have the same cardinality, we can come up with a function from the integers to the even integers that is both 1-to-1 and onto. I'm going to use the definition of how we get an even number, right? F of X is equal to 2X. We're going to show that this is both 1-to-1 and onto. And I'm going to do it in this space over here, where I'm going to try. So we will prove Z and 2Z have the same cardinality by finding a bijection between Z and 2Z. Let F from Z to 2Z be a function defined by F of X equals 2X. We're going to let A and B be integers and assume F of A equals F of B. Then 2A equals 2B, and it follows that A equals B. So F is 1-to-1. All right, now we're going to do the onto-ness. So we're going to pick an element y in 2z. And we got to go construct our x. So I'm going to move over here and do that. So y is equal to 2x. So that means that y over 2 is our x that we want. And the question is this an integer? Well, y was even, so yeah, it is. Because y was even, then dividing it by 2 makes it still be an integer. You couldn't do this the other way from 2z to z because that doesn't work. So you need to go this way. All right, so we're going to let y be in 2z and suppose x is equal to y over 2. We're going to notice that y over 2 is an element in z. Notice, again, maybe don't say notice again right there. Then, now, let's go with now. F of x is equal to f of y over 2, which is equal to 2 times y over 2, which is y. So since we found x in z such that f of x equals y, f is onto. We found a bijection between z and 2z. Therefore, cardinality of z is equal to the cardinality of 2z. Ooh, it's hard for me to write those next to each other. So that's how you do this. I think on your homework, you'll get to do this with like the odd integers and even integers maybe. But it's kind of a fun exercise to come up with a function and make sure your function actually works, and challenging but fun. So now we're going to do the integers and the positive integers, which is also weird, but again, these are both countable. If you can make a list, if you could start counting, then they are countably infinite. So like if eventually, if time was no restriction, then, and you could keep counting forever, that's countable. Okay. But you can make a list. That's the important thing. If you can make a list, then you can number the list, which means that you are counting them and they're countably infinite. All right, so we are looking here. We have the integers and the positive integers. So we want to come up with a function that's both one-to-one and onto between them. And this is kind of fun, I guess. We are going to go from the integers. So we're going to come up with a function f that goes from z to just z plus. I'm going to take the positives here and I'm going to map those to the even integers. And then I'm going to map the non-positives to the odd ones. Okay, so the way this is going to work would basically, it's like a sort of a counting from 0, either even or odd, depending on. So I'm going to make this list to sort of demonstrate this thing. So we have our domain is the integers. So 0, 1, 2, 3, 4, 5, 6, whatever. -1, -2, -3, -4, etc. So we're going to map from the integers into the positive integers. I'm going to map the positive integers to even ones. So let me see, what color should I use here? This 0, no, positive. So 1 is going to map to 2. 2 is going to map to 4. Now I'm counting my evens this way. 6, 8, 10, 12. And I'm going to go this way and get my odds. So 1, 3, 5, 7, 9, and so on. So this goes on forever, both ways. But you can see that this would work, right? If I just count all of the positive integers, I count them by twos basically, and I can count all of the negative ones or non-positive ones also by twos, but with the odd numbers. This would eventually get everything, which is great. And then to make this function actually look nice, we can write this as a piecewise function where we go to 2 times the integer. See, that's what's happening. Yeah, with me. So 2 times the integer when x is positive. Let's see, for going this way, 0, 1. Goes to 3. So I'm going to get bigger. So we're going to subtract and subtract with negative. So 1 minus 2x when x is less than or equal to 0. So let's try that. If we do 1 minus 2 times 0, we get 1. If we do 1 minus 2 times a negative 1, that's 1 plus 2, which is 3. Okay, that's good. 1 minus 2 times a negative 2, that's 1 plus 4, which is 5. Okay, so that works. So this is the function here, and you could prove that this is 1-to-1 and onto. We're not going to right now, but you can like look at this and see that it's lining up like this. There's one arrow to everything and one arrow from everything. All right, so again, I keep saying, like, if you could make a list, then it is countable. We are actually going to do this between z plus and q plus. So remember, these are the positive integers, and this is the positive rational numbers. But this idea can be expanded to two negatives too, but this is just to sort of make the process easier looking. All right, so the way we're going to do this is, like, let's pretend that we had maybe lines in a spreadsheet, right? So on the first line, we're controlling the first row, we are increasing the denominator. So rational numbers, remember, are the ratio of two integers. So we're going to make a table of all possible rational numbers. So the first row is going to have a 1 in the numerator everywhere. The denominator is growing. The second, and this would just continue on forever, right? The second row will have a 2 in the numerator, sorry. And the denominators, are going to stay the same that they were before. Now notice I have written some of these, I've hit some rational numbers twice already, right? 1/2 and 2/4 are the same. 1/3, 2/6, that's the same. This is 1, and so is this. So there's going to be some redundancy here. But I will eventually, if I continue this on forever, I will get all positive rational things. I'm going to keep going, making, 2 more rows. So, 3/1, 3/2, 3/3, 3/4, 3/5, 3/6, etc. And then 4/1, 4/2, 4/3, 4/4, 4/5, 4/6. Again, lots of duplicates happening. That's okay. If I could go on forever, I'm going to have duplicates, sure, but I will also have every possible rational number listed. And because I made this list, that means it's countable. But let's do come up with the function, the mapping for how this is going to go. So this is interesting that you're going to go here. Let me get a different color. Pink. So this is going to be your first thing in the list. And then you're going to move this way. And this will be your second number in the list, 1/2. Then you're going to diagonal go here. This will be your third entry in the list. Then go down this way. That'll be your fourth entry in the list. And we're going to scoot up back to the top. We're going to skip any duplicates. So we're going to skip 2/2 because we already counted 1. So, and this will be your fifth entry. We're going to scoot to the side. That'll be your sixth. And then you're going to, again, scoot down diagonally, skipping any duplicates, which there are not any right now. So you're going to get all of those. Those are your 7th, 8th, 9th entries. And then you would go down here to the, to 5/1. And then you would scoot back up, skipping any duplicates, which 2 is 1, 1 is 1, 1/2 is 1. So you go all the way back up here to 1/5. And that would be your 7, 8, 9, 10. That'll be your 11th entry. And so you could do this forever and get all possible rationals, and you're mapping from, the integers into and onto the positive rationals. So these are both countable. They're both countably infinite, and that is that. Okay. So the the rationals here and the real numbers, I'm gonna spoiler alert here for you. These are countable because we just made a table so we can count them. These are not countable. So these are uncountably infinite. The question is, can you list the real numbers? And the answer is no. There are actually infinitely many numbers between 0 and 1. Like on this interval 0 to 1, there are actually infinitely many numbers, and uncountably infinitely many. So this is the diagonalization thing. Cantor did this originally. This is kind of confusing, and not being able to see your faces is going to make this look weirder, but we're going to suppose that we can. This is a proof, by contradiction. Let's suppose we can make a list of all possible numbers between 0 and 1. So this is a decimal. So we have A11, A12. These are going to be, these are just numbers in a list. We're supposing we can list all of them in this table, a table that is going to have, all of the numbers between 0 and 1. We're just organizing them in this way so we can make a point. This keeps going, A31. You kind of get the picture here. And then the last one is the nth row and the nth entry here. So we have point ANN, AN1, I meant AN1, AN2, AN3, AN4, AN5, and then ANN is the last thing. All right, so what we want to do is pick off a number that is, we're gonna, these guys are diagonal entries. There would be, these go on for, so you're looking at these diagonal entries, A11, we're coming up with this number D, which is A11, A22, A33, A44 to ANN. We'll call this D1, D2, D3, D4 for diagonal entry 4, and so on, DN here. So this is our number D. Maybe I will call this let's call this guy X. I don't know. Okay, so D is this diagonal, this number that is like this. And we are basically coming up with a number that hasn't been listed already. So in this thing, DN is going to be 1 if ANN is not 1. And it's going to be 2 if ANN is 1. So what this does is we have come up with a number that's not in the list. So this number D is going to be different in at least the whatever spot. So in at least one spot, this number D is going to be different than anything in the list because we have changed that entry. So if we're looking at D3, right? If it was 1, we're changing it to 2. If it wasn't 1, we're changing it to 1. So this number D will be different than this third entry number at least this spot. And if you change the fourth one, right, then this number D, which is a decimal, right? This number D will be different than the fourth entry in our list at least that spot. So every number here that we could, this D is different than all of these numbers in at least one entry in this like decimal. And so you have come up with a number that wasn't in the list, which means you can't list them, which means there are infinitely many numbers between 0 and 1, and therefore, obviously, there are infinitely many real numbers, because even on that tiny interval, there are infinitely many of them. So you have come up with a number, you have created a number D that is not listed in what you thought would be the list of all possible numbers between 0 and 1. So look in the book for more explanation of that, or to read the history of that sort of argument, the levels of infinity argument there. We are going to start talking about 5.5. I'm not going to go too terribly far into it because 5.1, I mean, I don't want to do induction through Zoom. So we are going to just start the sequence stuff, and then we'll kind of see where we go. But so a sequent is a function whose domain is all integers between two given integers, or all integers greater than or equal to a given integer. That is a lot of words. Usually we start at, usually this is starting at 1 or 0. You get a, it's a list of things that are happening. This is going to make sense when we do examples. A sub n is the nth term of a sequence. Use the curly braces to represent the entire sequence. These are, for you computer science people, one-dimensional arrays. And so that's how this goes. So a sub n, the nth term in this sequence, is 1 over n. So this you could write as a sub n, or 1 over n. If we were trying to make a list of this for this one-dimensional array, a1 is 1, a2 is 1 over 2, a3 is 1 over 3, and so on. And so we could actually do this as that array. So 1, 1/2, 1/3, 1/4, all the way to 1 over n. So this is your sequence, a sub n. A sub n here on number 2 is 2 times -3 to the n plus 5 to the n. So a1, the first entry in the sequence, would be 2 times -3 to the first plus 5 to the first. So that would be a -6 plus 5, so -1. A2 is going to be 2 times -3 squared plus 5 squared. So that's what 2 times 9 is 18, and 25 is 43. A3, you would have 2 times -3 cubed plus 5 cubed. That's 71. We're just going to trust that. So if you were making your array here, you would do it like this: -1, 43, 71, ... And then the nth entry is 2 times -3 to the n plus 5 to the n. Okay. Number 3, we have this sequence of numbers that follow this pattern, where the nth entry is n plus 1 to the n plus 1. So for us, a1 here is 1 plus 1 to the 1 plus 1. So it's 4. A2 is 2 plus 1 to the 2 plus 1. That is 27. 3 cubed. And then you got 4 to the 4th, which is 256. So your sequence looks like this: 427, 256, dot, 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 dot. Okay. Now sometimes you're going to be looking at the sequence and you're going to need to come up with the sequence, that the actual like closed form version of the sequence, or the formula, right, for what this looks like. So you have this 1/4, 2/9, 3/16, 4/25, 5/36. So the way I'm looking at this, these are counting n's, and these are n plus 1's squared. So 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. Yeah. So this sequence is defined like this: n over n plus 1 squared. Or this is with for n greater than or equal to 1. Or you could do like n minus 1 on the top and then n squared on the bottom, as long as your n started at 2. So either one works here. A sub n, I like the first one better. N plus 1 squared, n over n plus 1 squared. All right, so on number 5, you notice that there's a negative that's popping up every other term, basically. So we're going to need to do something with that. That's a -1 to a power, because the even powers, it goes away, and the odd powers, it doesn't. If we start counting at 0, because this does. So let's do n times. Now I need, when I do this, so this would be, 1, the 0th term, the first term, second term, the third term. Okay. Now when I do this, I would like for, on the evens, the negative to appear. So if I make this an n plus 1 power on that -1, the even entries, the even ends, would have an odd power of -1, which would make that -1 show up. So we do 0 times -1 to the first. Well, that's still 0. If we do 1 times -1 squared, that would be 1. If we do 2 times -2, -1, sorry, to the third, that would be -2. Okay, so this works. So your sequence here, your series here, sorry. No, sequence. Your sequence here is n times -1 to the n plus 1, starting at n equals 0. Okay. Now finding those is, can be very challenging, but yeah. Now for summing up a bunch of terms in a sequence. So summation notation, m and n are integers, m's less than n. Then you have this summation, the sigma notation. This is a summation from the k, where the mth entry to the nth entry of this sequence. So that means you're going to take a bunch of letters here makes this awful, but let's suppose this is a 1, right? Or 0. Then this is a 0, a 1, a 2, a n, right? So it's just adding up a certain like bit of terms from the sequence itself. So let's do some of those in practice, what that looks like. Again, you have a starting like index and an ending one, so you know which entries that it is that you're adding up. So here we're going to go from k equals 1 to 5, and we're going to add up the first, second, third, fourth, and fifth entries in this sequence. So k is the sequence is just 1 here, so there is just the number itself. So you have 1 plus 2 plus 3 plus 4 plus 5, and that is 15. Okay, so this one, the entries are k squared. So we're looking at 1 squared, 2 squared, 3 squared, and I'm stopping when k is 4. So I'm adding all of those things up. That is 30. So it's the sum of the first 4 numbers squared. This one, we're going to expand this thing. So we're going to start at 0 for the I, and we're going to count up to n. So when we start at 0 for the I, we're looking at -1 to the 0th power over 0 plus 1. That's the 0th entry, right? And then the first entry would be -1 to the 1 over 1 plus 1. And then we're looking at -1 to the 2 over 2 plus 1. And then -1 to the 3rd over 3 plus 1. And then some dots till we get to the nth term, and that's where we would stop, -1 to the n over n plus 1. And then this written sort of nicer, simplified, whatever, this would be, oh goodness, that's anything to the 0th power is 1. So you're looking at 1 over 1 there. So that's 1. And then this one, we're looking at -1/2. This one is a positive 1/3, and then a -1/4. That would be a positive 1/5, but whatever. Okay, so the nth term is -1 to the n over n plus 1 still. Okay, so the summation notation there, you're just adding up all of those parts in a sequence. That's an alternating series, folks. For those of you in Cal 2, that is probably what you're doing right about now. The summation form for this one, we're gonna write what it is. So you have 1 over n plus 2 over n plus 1 plus 3 over n plus 2. So it does appear that we maybe are counting up here. But if I'm looking at this, it's going to be easier for me to call this the 0th, the 1st, the 2nd entry. So on the bottom of my summation thing here, I have n plus I, and I'm going to start I at 0. So this is n plus 0, this is n plus 1, n plus 2, n plus n is what it ends with. So we're going to count all the way up to n. On the top, I have my I plus 1, right? So I have 0 plus 1, I have 1 plus 1, I have 2 plus 1. So if this is the 0th, the 1st, the 2nd, sorry, that did not, hold up. Let me sort of get rid of some of this. So the top is obviously 0 plus 1. This top is 1 plus 1. This top is 2 plus 1. So if this is the 2nd entry, or when I is 2, then this works. So you're looking at I plus 1 on the top. And then test it, obviously. So the 0th thing, I would have 0 plus 1 over 0 plus n. Okay, that's 1 over n, that's good. And then when I is 1, I have 1 plus 1 over n plus 1. Okay, that's 2 over n plus 1, that's good. When I is 2, I'm looking at 2 plus 1 over 2 plus n. Okay, so this works to give me each of these things in the summation notation. So that is that. I think that I'm going to stop there. I don't want to teach induction via Zoom. This is arguably the strongest tool that I will teach you, so I would like to do it in person. Okay, so we're going to stop there. Let me know if you guys have any questions. You are going to be able to do that. You will be able to finish your written homework number 8 to turn in on Tuesday. So if you need anything, let me know. Thank you very much.